So far in dynamics, we've been talking a lot about this concept of kinematics, and some of that was revisiting some of our concepts from physics class, but what our kinematics portion has been covering up to this point is essentially those relationships between position, velocity, acceleration, and time, how we can move between those, and how the geometry of the problem affects what's going on. And now what we're going to do is move a little bit more into this combination of physics and statics by talking about kinetics. And kinetics is this relationship between the change in motion of a body, so how that body is accelerating, how that body is moving, how it's changing, and the forces that cause the change. And really the whole basis for this idea of kinetics is Newton's second law. Newton's second law, and my favorite law because it gives us a very handy equation, deals with the relationship between the change in motion of the body and the forces on a body, which is going to be that our force equals mass times acceleration. And of course these are in vector form. So our force equals mass times acceleration, where we have this unbalanced force, we have non-zero forces that are causing some kind of acceleration, where we have the mass of whatever is moving, whatever is being accelerated, and then of course the acceleration that body is experiencing. And this mass here is really a measurement of inertia. And we'll talk about this a little bit later in the course, but sometimes you'll hear this like resistance of a particle to change. It's resistance to a change in motion, this inertia. So this mass kind of represents the inertia of a body, of it being in a steady state. So, for example, when you're driving in a car, right, and the car suddenly accelerates. The car suddenly starts going forwards much faster. But your body, what you feel when the car goes forwards much faster is you get pushed back. Now, there wasn't actually anything pushing you back. It was the fact that your mass that was sitting there had an inertia that was not moving, and then all of a sudden your inertial frame, the frame around you, started moving and accelerating you, so you felt this like push back, and that was from your own mass wanting to stay where it was, while the system around you is being pushed forward. So that's a very long-winded explanation for the concept of mass and what inertia is, but we'll talk about that a little bit more later too. The most important thing right now is that this bad boy is what we're going to be using. This is our main equation of motion. That's what you'll hear it referred to as a lot. Newton's second law, equations of motion, that we use to relate our forces on a body to the acceleration of that body. And this body that we're talking about, right now we're really just going to be talking about a particle. We'll talk about rigid bodies later on in the course, but right now we're just talking about for a single particle that we say does have mass. We'll be experiencing a force, we'll be experiencing an acceleration, and we'll be doing essentially statics type problems, but instead of all of our forces being set equal to 0, as we do in statics, because we were in static equilibrium, meaning that we were not accelerating, we were either not moving or at constant velocity, the step up that we take in dynamics is that now F equals ma. When we take a summation of forces, now it equals mass times acceleration. Right, so it's just a little bit more complicated, where we can still use this concept from statics of taking sums of forces, but now we can also integrate that with the kinematics that we've been talking about to find acceleration relationships and find these relationships between force and acceleration. So how do we approach these? How do we kind of like look at these problems? And of course we'll do some examples and it'll make a little bit more sense. But let's talk about like a general procedure for analysis when you're looking at a problem, when you're looking at a kinetics problem. And so usually you're finding some relationship between force and acceleration. Maybe you're finding a force. Maybe you're finding an acceleration. Maybe you're going back and you're finding a velocity or a position. Right? But we're going to use these relationships to solve problems. So our general rules, general procedure for solving these types of problems is that first we're going to set a coordinate system. And this is, as we worked with in kinematics, this could be a rectangular coordinate system. Maybe you're using a curvilinear system, so you need to use a normal and tangential kind of coordinate system, or a polar coordinate system. Maybe the motion is entirely rectilinear. So just being aware, what is this coordinate system that would be best to use for a particular problem? You get to choose that. Then we're going to do favorite thing in the whole entire world, and we're going to draw a free body diagram. That's right, it's come back from statics. We did not leave it in the grave in statics. It is back. It is here to haunt you. It is going to be in every single one of these problems. If you are not drawing free body diagrams, you're hurting yourself more than anybody else. All right, free body diagrams are going to be really, really helpful so that you can see all of the forces acting on this particle. Right, so we're going to put a big old star here because what we're going to do is we're going to draw a free body diagram. Right, so that's your force diagram. So whatever forces happen to be acting on this particle, maybe there's a normal force, maybe the body itself has a weight, maybe something is pushing on it, there's some other force that's shoving it, for example. So we're going to draw a free body diagram to capture all of those forces. And with that, it can also be really helpful to draw what's called a kinetic diagram. And this is a little bit of our new piece here. But a kinetic diagram is essentially kind of setting your coordinate system and also indicating the direction of acceleration. So, for example, this little particle that I drew over here that had all these forces on it, let's say that this guy is moving to the left, right? Because it has that F force on it. Let's say that that F force there is causing an acceleration to the left. So a kinetic diagram will be, I guess I could have done this in a different color, but let me just draw a line here. A kinetic diagram will show mass times acceleration, or just the direction of acceleration. Sometimes it'll just say A. And indicating the direction, and sometimes it'll have the coordinate system in here as well. So maybe it would be like Y, X, if we happen to be in a rectangular coordinate system. So that it can give you a reference of which way our acceleration is going. Next, we're going to use our equations of motion. So use our equations of motion. And what these really boil down to is just going to be sum of forces equals mass times acceleration. But this does work just like statics. So if you're, for example, in a rectangular coordinate system, the XYZ coordinate system, you're going to have sum of x forces equals mass times x acceleration. Sum of y forces equals mass times y acceleration. Sum of z forces equals mass times z acceleration. You're breaking them up into those components still, as we saw in statics. We're just doing this time equaling mass times acceleration. So we're going to use each of those equations of motion to solve for any forces or accelerations that we don't know, that we're trying to find. So we can use this to solve for forces or acceleration unknowns. And then finally, if we can't get enough information from what we have so far, we can always go back to our kinematics that we've discussed. So that was all of chapter 12 in our Hibbler book. But this is all we can apply the kinematic equations. Apply kinematics to find anything else that we need. So if we need like a velocity or position or time or any of those relationships, we can always go back and use kinematics in these kinetic problems and trying to solve for these forces and accelerations that are acting on a body. One quick note I want to make about units in this. Right, so we're dealing with this force equals mass times acceleration. So I think it's important that we just touch on units. And let's look at our SI units. So our SI units for force equals mass times acceleration. This one probably feels a little bit more common to us. We use it a lot during statics. You see it a lot in physics. Our force being in newtons. That's the standard unit for force in SI units. Mass is in kilograms, and acceleration is in meters per second squared. And gravity in SI units is 9.81 meters per second squared. What we may not be as familiar with, or we may not have seen as much of in working in statics or physics classes, is our US units, our US customary units, which are things like feet, inches, blah, blah, blah. So in our US customary units, force is measured in pounds. And you'll see this as LB. This is pounds. Sometimes you'll see it as the letter P. That's really only if it's in like PSI, pounds per square inch, that kind of thing. Usually you'll see LB, LBS sometimes. Occasionally you'll see it as pounds-F or pound force, because there is like a pound mass and a pound force, but typically pounds are always going to be our force unit. So you'll see it as pounds, pound force. If you encounter somebody who is 100 years old, you may see them use this symbol for pound. That's the pound key. The hashtag sign is a pound key. It stands for pound. It's pretty archaic though. Just letting you know, you may see it that way. And then we have our acceleration. Our acceleration probably feels a little bit intuitive. It's going to be feet per second squared, where our gravity in US units is 32.2 feet per second squared. But what is this mass? What is the unit of mass? If we've already used pounds, and we know pounds is a weight, it's a force, what is mass in our US units? It is not something we commonly use, but it does have a unit, it does exist, and it's something called a slug. We touch on this super briefly in statics. But the standard unit of mass in US units is something called a slug. And so something that is 32.2 pounds of force is a slug. And the way you almost always find this, the way you almost always see the mass term written out in these equations of motion, is you're pretty much never given anything in slugs. We are always weighing things, we are always working in pounds pretty much. We're pretty much always using the pound force. So for our mass term, we're almost always finding it by taking whatever the thing weighs and dividing by gravity. This is almost always how you're going to use the mass term when you're working in US units. You're going to take how much the thing weighs, divide by gravity, which is really just a rearranging of this F equals ma equation. But just know the standard mass unit in US is slugs. Yes, it sounds just like the animal, but it is slugs. And you'll find that by using mass equals weight over gravity. So now that we've kind of talked about these general ideas, the general idea of kinetics and these equations of motion, let's talk about how we're going to apply them and do some examples. So we're going to start with a rectangular coordinate system. And to give you just a few tips before we launch into our example here, give you a few tips for working in our rectangular coordinate system. So we'll call this equations of motion in rectangular coordinates. And I didn't plan this out very well. Sorry, I ran out of room. So those are x, y, z coordinates. So just like in statics, we can break these out into their individual coordinates for the equations of motion. So that's going to be sum of x forces equals mass times x acceleration. Sum of y forces equals mass times y acceleration. And sum of z forces equals mass times z acceleration. And we're going to use this in combination with our kinematics to solve problems. Now, a couple of things we may want to remember from statics, or from physics, or from wherever you learn these things, that may appear in these problems. Friction. Friction is a thing that commonly appears in these problems. Our friction force is mu, which is the static coefficient of friction, times the normal force. We may also see springs. The spring force is going to be K delta S. You'll also see this as negative K delta S, but at this point I'm going to assume that you're smart enough to determine the sign on your own, and I'm not going to babysit you with adding a negative sign here or not. F equals KS. And then our kinematic equations that we can use, that we had talked about previously, we were solving all of those kinematic problems, is if our acceleration is not constant, we know that our A is dv dt, we know that V is ds dt, and we may have problems where acceleration is constant, so we can use those kinematic equations of V equals V naught plus AT. S equals S naught plus V naught T plus 1/2 AT squared. V naught, nope, not V naught, sorry. V squared equals V naught squared plus 2A S minus S naught. Right, so those are if we have constant acceleration, which is possible. It could be changing acceleration, it could be constant acceleration. We will have to determine, based on what the problem tells us, which set we can use. If we can use the constant acceleration, or if we have to use our integration derivation related rate set for acceleration, position, velocity. So with all of that in mind, now let's go ahead and take a look at some examples of what we're talking about instead of dealing with this in the abstract. So let's take a look at this example problem. So in this problem, we've got a 50 kilogram crate as shown, which rests on a horizontal surface for which the coefficient of friction is mu equals 0.3. If the crate is subjected to a 400 Newton towing force, determine the velocity of the crate in 3 seconds if the crate starts from rest. So what we're shown in this diagram is really the action that is happening at the 3-second mark. So initially it's no force, it's just the box sitting there. Then suddenly that 400 Newton towing force shows up, that little yellow arrow shows up, and we are finding that velocity after 3 seconds. So it's overcoming that initial friction, it's overcoming that initial inertia of not moving, and we're saying, all right, it's moving, it's got a velocity. What is it? This is what we're trying to find. So what we're going to do is we're going to set up our equations of motion with our F equals ma, and we're going to combine that with our statics skills of problem solving, and combine that with our kinematics that we've been doing so far in the class to bring all of this together this acceleration, forces, velocity, time, all of these things together to solve problems, right? We're going to be able to solve a lot beefier problems now, combining all of these different little pieces that we've been working on up to this point. So let's pull out everything that we can see about this problem. So if I just read through and pick apart what I see that looks important. 50 kilogram crate. That sounds pretty important. I'm going to put that down. That's our mass of our crate, right? The mass of our crate is 50 kilograms. The crate's shown on a horizontal surface. The coefficient of friction is mu. And this is kinetic friction. My K got dropped there, but there is a K in there. Our coefficient of kinetic friction is 0.3. Then we have that crate subjected to a 400 Newton towing force that shows up in our diagram on the left. We want to find the velocity of the crate in 3 seconds. So we're finding v at 3 seconds. If the crate starts from rest. So we know the initial velocity is 0. And we're working in SI units, so, I mean, not that my units really matter here, but it's 0 meters per second. So again, the way I want to solve this is I want to set my coordinate system, draw my free body diagram, draw the kinetic diagram, set up my F equals ma, and do any kinetics I need that's left over to solve. So breaking that down, one, we're going to establish the coordinate system. And we already said all of these problems that we're going to work on in this video are in the rectangular coordinate system, so it is kind of given to us. But we'll go ahead and just denote that we're working in an XY coordinate system here. And then we're going to draw our free body diagram. So our free body diagram, I'm going to come over and draw it right under here. Our free body diagram of our crate, who is acting like a particle. It has a 400 Newton force on it, acting at that 30-degree angle from our x-axis. It also has a weight, right? We know that this thing weighs 50 kilograms, has a mass of 50 kilograms, which means it has a weight of 50 times 9.81. Okay, that's going to be our weight of the box there. Because it has a weight and it's sitting on the floor, there's a normal force acting up against the crate. It doesn't fall through the floor into infinity. Got that normal force. And is there anything else that we're missing? So we have that coefficient of friction, means there is going to be a frictional force. And remember, our frictional force acts in the opposite direction of which way it's going. Right? So since it's being pulled to the right, our friction force acts in the opposite direction there, to the left. Right there underneath the crate. I guess let me draw this crate in a different color so you can kind of see. Nope, just kidding. That does not look better. Sorry. But those are all of our forces. Those are all of the forces that go into our free body diagram. Got the weight and the normal force, the towing force, and the frictional force. Those are all of our external forces and internal weight force, really, that contribute to our free body diagram. Now, if we were to make a kinetic diagram for this guy, that's going to tell us which way our acceleration is going. So here's my little guy. And because of that towing force, my guy is going to be moving entirely in the x direction, right? This towing force doesn't actually lift the crate off the floor. He's not accelerating upwards anywhere in the y direction. He is just being pulled along the floor. Even though that force here, this 400 Newton force, is like pulling upwards somewhat, but not enough to leave the floor. We're going to assume it's being dragged and accelerating only in the x direction. Only in the x direction. So that's what our kinetic diagram is telling us. Now that we have that, we can apply our equations of motion and set up our kinematics and see what we can solve. So again, those equations of motion, I'm going to do my sum of forces in the x direction equals mass times acceleration in the x direction. Sum of forces in the y direction equals mass times acceleration in the y direction. So my sum of forces in the x direction, I'm going to pull those off of the free body diagram. So my x components, I have the x component of the 400 Newton force, so 400 cosine 30. And then my only other x is going to be the frictional force. That's in the negative x direction, so minus the frictional force equals m times ax. If I look at my y, sum of y forces, I'm going to have the y component of that 400 Newton force, 400 sine 30, plus the normal force that is pointing upwards, minus the weight of the crate. So that's that 50 times 9.81 equals m times ay. Now thankfully, because of our handy dandy kinetic diagram here, I can see that my acceleration is only in the x direction, which means my acceleration in the y direction is 0. So I can go ahead and substitute that in these equations, right? My ay is 0 here, and for ax, I'm gonna put a. That's gonna be our overall acceleration. So now that I know in my fy, right, in this equation here, now that I know this side equals 0, I can actually solve for n. He's the only variable that's unknown now. I know what the mass is, right? I know what the mass is. It's 50. It doesn't matter because this side goes to 0. And I know my components here. I know my components here. So if I solve this for n, I'm going to get n is 490.5 minus 200. So the normal force is 290.5 n. And that it's a different n. It's a different n at the end there. That's newtons, right? So my normal force is 290.5 newtons. Which is excellent because what I can do is I can use this normal force value that I got to relate to my frictional force. Right? We know friction force is mu times n. So my friction force, what do we say mu was? 0.3? 0.3 times 290.5. So the frictional force is going to be a number that I do not have in front of me. So I'm just going to leave it like that. I did not type it into my calculator. That's okay. Let's just put it in. Let's put it into our, let's make a little substitution. We're just going to put this guy in here. Sorry, I'm not going to bother to type it into a calculator right now. We can do that at the end. If I take my x equation, 400 cosine 30 minus the frictional force, 0.3 times 290.5 equals mass times acceleration. The mass we know is 50 kilograms, and we said ax is the overall acceleration, which is great, right? Now a is the only thing that's unknown in this equation, so I can go ahead and solve for a. Now I'll punch it into a calculator, and I get 5.185 meters per second squared. Okay, so we're getting somewhere, right? We were able to use all of these F equals ma, relate this free body diagram to this new kinetic diagram where it tells us the direction of our acceleration, able to figure out all of our forces, able to figure out all of our accelerations. But now what the question has actually asked for is to determine the velocity of the crate in 3 seconds. Determine the velocity of the crate in 3 seconds. So we're done with doing new stuff. It's just going back to what we've been doing for the last few weeks, applying those kinematic relationships, right? If I know my acceleration in the x direction here, I know this acceleration is constant. Right? There's no t's in here. Since p is constant, this is a constant force. Right? This guy right here, he's a constant force. All of these forces are constant. The forces themselves are not changing. It means that the acceleration will not be changing. So this is a constant acceleration. And since this is a constant acceleration, even though we could go ahead and do the a equals dv dt, if you don't feel like taking an integral, we can clock this as constant acceleration and know that we can use the kinematic equations. V equals v naught plus at. So v equals our v naught. It said we start from rest, so we know initial velocity is 0, plus my acceleration we just found was 5.185 times the time, which we said we wanted to find this at 3 seconds, times 3, means that our velocity, what we've been looking for this whole time, velocity at 3 seconds is 15.6 meters per second. All we're doing is creating these relationships, making a free body diagram, making the kinetic diagram, relating force to mass times acceleration. We're having to find all of those multiple forces, break them up into components, find our various accelerations, find those in the kinetic diagram, and then we can go back to our kinematics and solve for anything else that we have left to solve. Let's take a look at a little bit more complicated example. For our next example, we've got a lot of words here. So we've got the baggage truck, which is, if you've ever been to an airport, there's little trucks that haul all the suitcases from the plane to the building. These are the baggage carts. So the baggage truck A has a weight of 900 pounds and tows the 550-pound cart B and the 325-pound cart C. For a short time, the driving frictional force is developed at the wheels of the truck is FA equals 40 t-pounds, where t is in seconds. If the truck starts from rest, determine its speed in 2 seconds. Also, what is the horizontal force acting on the coupling between the truck and cart B at this instant? You're going to neglect the size of the truck and the carts. So anytime you see that little note at the very end, neglect the size of truck and carts, you're treating this as a particle. You're going to treat it as it's just infinitesimally small and compared to the forces acting on it. You're just treating it as a single point in space, more or less. So we're going to treat this each of these as a particle. And let's ignore the second part of this for now, but for this beginning, we're just going to see if the truck starts from rest, determine its speed in 2 seconds. So let's deal with that first part first. So as we can see, we kind of already have a free body diagram for this guy in the diagram they gave us, right? We've got our 900-pound truck, the force of the 550-pound cart B, the force of the 325-pound cart C. We have the normal forces pushing up from the ground onto these carts. And we also have that frictional force, FA, that they describe, although they don't give us the FA equals 40t. I'm going to add that over here. FA is 40t in pounds. So let's see, what in our statement here didn't get included. So we have the truck weights. Truck is driving frictional force is FA equals 40t. We've got that on our diagram now. if the truck starts from rest, that's a hint that v naught is 0. Determine its speed in 2 seconds. So speed, so seeking just the magnitude, not a direction, don't need a sign on it. So what is the speed when time is 2 seconds? So that's what we're finding. So it's actually going to be pretty similar to our last problem, right? Where we're finding a velocity given a set of force and acceleration circumstances. So we're already given the free body diagram. I'm not going to draw this again. It's given to us here. But we don't have the kinetic diagram, and that kinetic diagram will show us kind of how this thing is moving and what we're treating as the positive acceleration. So looking at these guys, I'm going to say, and I'm just going to use the truck, I'm going to draw a little block to represent the truck here, that our truck is moving, it's accelerating to the left, right? That's the way the truck driver is driving the baggage truck. So that's going to be the direction of our acceleration. And it's only in the x direction. This is linear. It's just I'm not very good at drawing. Right, so our acceleration, here's our little kinetic diagram. Our acceleration is going to be to the left. So we're going to use that as our positive assumption for our acceleration. And then we're going to go ahead and set up our equations of motion. So we did free body diagram, kinetic diagram. Now we do equations of motion. Our F equals ma. And in this case, we really only need to be looking at our x components here. Sum of fx equals max, because there's only acceleration in the ax direction, right? None in the y direction. There is no z direction given. So really we only need the one single equation of motion. Sum of x forces equals mass times acceleration. So taking a look at our free body diagram, what are my x forces? And really I've only got the one. I've only got 40t. Only got 40t. And it is moving in the same direction as my acceleration. Right, so I'm just going to use a convention that I'm going to say that this way is positive. To the left is positive. For my acceleration and for my force there. So my force is going to be 40t equals mass times acceleration. So my mass, remember again for US units, which is what we're working in because we have pounds, we're going to take the weight and divide it by gravity. So the weight, I need to include all of the weights, right? Everything in this chain is being propelled forward. That's going to be my 900 plus the 550 plus 325 all over gravity, 32.2. That's what's going to give me mass. And there's my acceleration in the x direction. So if I go ahead and simplify this number and get ax by itself, I'll get that my acceleration in the x direction is 0.7256 t. Right, just rearranging this equation that we made here. Now I want to find the velocity, the speed in 2 seconds if the truck starts from rest. So what I'm going to do is I'm going to use my acceleration equals dv dt. Right, I can't use a constant acceleration because I've got an acceleration in terms of time. It's not a constant acceleration. I'm going to have to use the integration form. So that'll be 0.7256 t times dt equals dv. I'm going to set up my integration to be from my time we start at time 0, and we're trying to find the speed at 2 seconds. So we're going from 0 to 2. And then for my velocity, we start from rest, so that's a 0 velocity, and we don't know what we go to, right? We're trying to find that, so we're just going to integrate to the general v. If I integrate my left side here, 0.7256 t squared over 2, I'm going to evaluate that from 0 to 2, equals v. And then I'll plug this in my calculator, so all I'm doing is substituting in the 2 for t. So I get 0.7256 times 2 squared over 2 equals v. My velocity, or my speed at that time, is 1.45 feet per second. I punch that into the calculator. So that is our speed. That's our speed at 2 seconds. 1.45 feet per second. Then we also need to find this part B. So we haven't done this part B yet. I'm gonna just call it part B because it's the second half here. What is the horizontal force acting on the coupling between the truck and cart at this instant? At this instant. So what I'm going to do is I'm going to draw my free body diagram, but now what we're looking at is taking a split here, basically. We want to know what the force is in this coupling right here. I'm going to draw my free body diagram, but with that split right there. So I have, here's the truck. It has the normal force A. It has FA is 40T. It has the weight of the truck, 900 pounds. And then it has the force in the coupling. I'm going to call this, I don't know, FC. Force in the coupling. And that's what I'm trying to find, right? Force in the coupling. Bear in mind, we're still accelerating, right? At this instant, we still have this kinetic diagram where we have acceleration going towards the left. So don't forget that that's still there. This is not a statics problem. You cannot just set things equal to 0 and solve it. You've got to remember that we're dealing with acceleration here. So for this guy, now I'm looking at just the truck. Sum of fx equals m times a. So my sum of x now is 40t minus that fc. And remember, I'm doing maybe opposite of how your brain's thinking because I said that my positive was going to be to the left in this problem. Positive is going to be to the left just because that's where my force and my acceleration were both pointing. So 40t minus fc equals mass. My mass again is weight over gravity, 900 over 32.2 times acceleration. And my acceleration at this instant, my acceleration ax, I have a relationship for that. It's 0.7256 t. 0.7256 times at this instant at the 2 seconds, right? At the 2 seconds, so we're going to plug in the 2. I'm also going to plug in the 2 here. I forgot to do that, but this is 40 times 2. And with all of this plugged in, it's just a matter of some algebra in order to find FC. So that force in my coupling, when I rearrange this and plug it into my calculator, I'm getting 39.4 pounds. All right, so we can see how this would be super useful to know what this force in the coupling is, to know what speed we're moving at after 2 seconds. You know, maybe that coupling can only withstand 30 pounds of force, and this would tell us that the coupling is going to fail, just as an example. So we can see how building on all of these physics skills and statics skills and calculus skills. They have all been base work, leading you up to more and more complex problems. And this will be base work for even more complex problems when you get into your junior and senior year of engineering school and you get into deeper specialties. It is all base work so that you can solve really complex problems to come up with designs, come up with solutions in ways that are physically possible. That's why we're doing all of this. Right? We learn all this math to keep stacking things and stacking things and stacking things so we can solve really complex problems. And let's do one ourselves. Let's do a complex problem ourselves. Let's take a look at our next example. Let's take a look at another example. Here we've got a 10 kilogram projectile that's fired vertically upward from the ground with an initial velocity of 50 meters per second. We want to determine the maximum height it'll travel if scenario A, atmospheric resistance is neglected, and in scenario B, where atmospheric resistance is Fd equals 0.01 v squared, where v is the speed of the projectile at any moment in meters per second. So I want you to go ahead, before we work through this together, I want you to go ahead and try it on your own. At the very least, part A should be very accomplishable. Right? I think you can figure out part A on your own, knowing everything we know now, and you might even be able to get part B. So go ahead, give it a try, pause the video, and when you're ready, unpause, come back, and we'll work through it together. Let's go ahead and look at part A here. So this part A, if atmospheric resistance is neglected, let's still go ahead and do the motion just to practice drawing a free body diagram and a kinetic diagram of what's going on here. So we have our projectile. It's this gray guy coming out of the cannon over there. And if I draw my free body diagram for him, here's my projectile. My free body diagram, all that's happening to him because he's up in the air is he is being dragged down by his own weight. Right, so here's my free body diagram. He's being dragged down by his own weight. Weight is going to be 10 kilograms times 9.81. That's it. That's the only force acting on him is gravity, really, his own weight from gravity. Since there is no drag. So looking at our kinetic diagram, we're trying to find max height. So our max height, when we fire up our cannonball straight up into the air, he is accelerating upwards until he reaches his max height, and then he starts to accelerate downwards, right? So he's accelerating upward. That's what's happening in our kinetic diagram. So what we're going to have here is we're going to have our equations of motion. If we go ahead and apply that, sum of forces Fc equals m times acceleration z. We're going to have, if we say up is our positive convention, up is our positive convention, then our force in the z, we only have the one force. It's that 98.1 newtons, that's the 10 times 9.81. In the negative z direction, right, going downwards, equals the mass. The mass was 10 kilograms times AZ, which means that our AZ is negative 9.81 meters per second squared, which this might have been obvious to you, right? This might have actually been clear to you actually that, oh, this is a projectile motion problem. Of course the gravity is going to be, like, of course the acceleration is negative 9.81. That's what gravity is. The acceleration isn't actually acting in the positive direction, it's acting in the negative direction. And this sign is what told us. This sign told us that, one, we should have known acceleration was not going upward. It's a projectile motion problem. There's only gravity acting on it, right? Only gravity. Acceleration is actually in the negative direction. So this is telling us that we assumed the wrong way in our kinetic diagram, and that our acceleration is actually in the negative direction. Which we know this is a projectile motion problem. So we could have skipped all of this nonsense right here. It's just a projectile motion problem. We could have skipped this and we could have just said, I know it's projectile motion. I know gravity is constant because we're on the Earth and it's a projectile that's going up and coming back down. So if I want to find this delta z, right, finding how high it went, finding that delta z, I can just use my kinematic equations, right? I can just use v squared equals v naught squared plus 2a delta z, where delta z is this thing we're looking for. We're looking for that height. It gave us an initial velocity of 50 meters per second. We know at the max height, remembering back to our projectile motion problems, at max height, velocity is 0. It's got to turn around to come back down, right? Velocity is positive and then it's negative. The velocity is 0 squared equals 50 squared plus 2 times negative 9.81, right? That acceleration is negative, as we proved through our equations of motion and as we know from our projectile motion problems. Negative 9.81 times delta z. So delta z, the height that it's reaching, since it said we started at the ground, we're going to assume that our initial z is 0. So the height that it's reaching is 127 meters. That's for part A, if we ignore that atmospheric resistance. But what if we don't? What if we don't ignore that atmospheric resistance and say, now let's take drag into account? Right, so drag is this concept of if an object is moving through the air, that the air provides some resistance. It doesn't just float through air. Air is made of stuff. It's not a vacuum. It has to actually go through physical material. And that physical material, that air, causes drag. So atmospheric resistance being the drag force of 0.01 v squared Newton. Let's go ahead and look at this part B. It's part B. Actually, I might just do it over this. Just delete this out. I'm going to redraw that kinetic diagram. Alright, so now for part B, since we're going to be taking into account this drag force, how does this drag force act on our object? Right, our object is going up into the air, and drag acts in the opposite direction of motion. So since this projectile is going up, our drag force is going to be acting downwards. 0.01 v squared. Our kinetic diagram, we can draw it either way now. We know for a fact that our acceleration is going in the negative direction, but bear in mind we're going to keep up as positive convention. Okay, we're going to keep up as positive convention. So now if I go to do my equations of motion, this actually kind of matters. Right, when I go to do my sum of forces in the z direction equals mass times the acceleration. Now I've got two forces here, two forces in my free body diagram. I have negative Fd, which I'm going to go ahead and just put in the 0.01 squared minus 98.1 newtons, that's from the weight of our projectile, equals mass, we know the mass of the projectile, it's 10 kilograms, times AZ. Times AZ. So we know, if I come and solve this, AZ is no longer constant. AZ is negative 0.001 v squared minus 9.81, right? Just dividing that 10 over to the other side. Acceleration is no longer constant. It is now in relationship with its velocity, which means we can't just use our projectile motion equations. We're going to have to use our integration relationships. So thinking back to our kinematics, those integration relationships, we've got one that relates acceleration and velocity to position, which is what we really want because we want to find that z value. We don't care about time. There's no time in this at all. So using our a equals v dt doesn't make the most sense for us here. What makes a lot more sense for us is a ds, where now our s is our position in the z direction, is v dv. This one makes a lot more sense for us since we have acceleration in terms of velocity. I can go ahead and substitute that in over here. Negative 0.001 v squared minus 9.81 ds equals v dv. I'm going to rearrange this, and I am going to go ahead and I'm going to substitute in my z's for my s's because that's the direction we're working in. Right? It's just a position. I'm going to say dz equals, and I'm going to divide all this stuff over to the other side, v dv over negative 0.001 v squared minus 9.81. And then I'm going to go ahead and do my integrals. I'm integrating from 0 to z. We start at the ground and we want to find out how high we're going. We're trying to find that height z. And then I'm going to integrate my velocity. We started, our initial velocity was 50 meters per second, and we're going to max height where our velocity is 0. So here we're actually integrating from 50 to 0. And this guy's kind of nasty. He's kind of not a fun integral, and he's one of those that just brings up old calculus skills that you gotta remember. And this one is a u substitution. U substitution. So that's where I'm going to take this entire bottom portion and say that equals u. U is negative 0.001 v squared minus 9.81. Take the derivative of that. Du is negative 0.002 v dv. And I can solve this for dv to plug it into that integral. So dv is du over negative 0.002 v. If I come back and I plug those into my integral over here, where if I solve the left side, it's just going to be z. It'll make our lives easier. We're going to have that integral of v, and then dv is getting substituted, right? dv is now du over negative 0.002 v. And in this bottom portion, we substitute that entire bottom with the u. And if I look here, these v's cancel out. So now I'm just integrating this 1 over negative 0.002 du over u. U over u. So that gives me a natural log. The integral of 1 over x is the natural log of x. Another special condition to remember. So we'll go ahead, we'll have that integral. I'll write it over here. 1 over negative 0.002, that is negative 500 ln of u, and then I'm going to go ahead and substitute this u back in and evaluate my integral at its original limits. So that's going to be negative 500 natural log of negative 0.002 v, nope, 001, sorry, 001 b squared minus 9.81 evaluated from 50 to 0. Whew, a long walk, a long walk. You plug in our 0 number, plug in our 50 number, plug that into a calculator. Evaluating those integral limits gives you z is 114 meters. Right, so it took a little bit more work, but we can see that when we have drag on that projectile, go up to 114 meters, whereas our projectile motion, which doesn't take into account that drag, I got rid of the number, but that number for projectile motion was 127 meters. Right, so when we actually have to take into account the physics of what's going on in the real world, we have to start accounting for things like drag. We're going to see that we're getting lower max heights. And we might have kind of expected that, right? A lower max height than the theoretical maximum in a vacuum. But this is really good for us to know, right? Because we are going to be engineers dealing in the real world. We're hardly ever going to be firing things into a vacuum. So we're going to keep dealing with more and more complex problems, but keep finding ways to build on what we already know, and every day get a little bit closer to those real world issues that we're actually working in real world physics, solving these problems to make other people's lives better, really. You want to do one more problem? We'll do one more problem. I've got one more. It involves pulleys. You know, if you like pulleys, if you don't like pulleys, then you should probably keep watching so that way you can get better at pulleys. We'll do one more problem with pulleys, just to give you another example. Pull together some more of those things that we've learned. Let's look at one last problem. Alright, here's our last problem, as promised, a pulley problem. It will be the last one we do in this video. I know they take a lot of practice, but it's good to review these pulleys, good to see lots of different examples of these. We'll look at this last one. Go ahead and attempt it on your own if you want, but I'm going to go ahead and talk through it. We've got a 100 kilogram block A that's released from rest. The masses of the pulleys and cords are neglected. Determine the acceleration of the 20 kilogram block B. Now, if your instinct, if your feeling inside is really like, let me do the kinematics. I know how to do the kinematics of the pulley. I can find those acceleration relationships. Let me start with that. That's great. You can do that. There's no problem if you want to start with that kinematics and then you want to do the kinetics with the free body diagrams and your equation of motion, F equals ma. That's perfectly fine. You can change the order around and find the different components in a different order. Do what kind of flow works best for you. And I'll go ahead and demonstrate that here. We'll go ahead and look at the kinematics first. Because maybe you really want to find those relationships between your accelerations, because we know that's what we're finding. We're finding the acceleration of block B. So let's go ahead and do that, just as if we were solving another kinematics problem as we were doing in chapter 12, section 10. So if I'm going to look at the kinematics of this guy, I have my pulley, I've got block A, and I've got block B here. And so we've got the 100 kilogram block A released from rest. As the pulley and cord are neglected, determine the acceleration of the 20 kilogram block B. So we're going to go ahead and assume, I'm going to assume that A is moving downwards. Right? And our positive convention for pulleys are always going to be movement away from our datum. That's what's going to give us the positive direction. Down is positive. So we have this distance SB from our datum here. They gave us the datum in the diagram. It was very handy. From our datum at this fixed point at D, we have length SB. And we also have this length, I'll call it SA. And we have one of those on either side. So if we're doing the kinematics for this, that's finding our length and then summing those lengths together. So the lengths that I have here are going to be my distance to A You could call it distance to c. You can label these things as you want. It's something that is clear to you. I'm using A because I'm finding that relationship between A and B and not necessarily A and C. They're kind of the same thing, but this is not my point. The point is, some of my lengths is going to be my SA plus my SA, because I've got this other one on the other side, plus my SB. That's the total length of this pulley system here. If I take a derivative, I'm going to get 0 is 2 times VA plus VB. And if I take another derivative, I'm going to get 2 times acceleration of A plus acceleration of B. So I can get the relationship between A and B. Acceleration of A is negative 1/2 times the acceleration of B. So this is the kinematics portion. We usually save for last. Fine if you do it first, because now we have that relationship between acceleration of A and acceleration of B. But how are we going to go about this other portion? Right? How are we going to go about the actual kinetics part? Well, let's draw some free body diagrams. Right? Start us out with some free body diagrams. So my free body diagrams, I'm going to have multiple that I'm looking at in this case. Right? I'm going to have a free body diagram at A. And this one might be kind of simple, maybe overly simplified, but it can be helpful to see. So if I look at my free body diagram at A, I have the block A that weighs, or that has a mass of 100 kilograms, meaning that it weighs 100 times 9.81. And it's got this orange cord connected to it that connects it to pulley C. So I'm going to call this tension 1, right? The tension of that orange cable. And if I look at B, I'm going to have something very similar. Right? So at B, I have the weight of B, which is the 20 kilogram mass times gravity, 9.81. And then I've got a tension in the rope at B. But notice that this is not the same tension. Highlight it. This is not the same tension as the orange cord. This is our brown pulley cord that goes all the way through here. That's our tension. So it's actually that our tension in this cord here is the same as in this cord here, isn't the same in this cord here, but not the same as the orange cord. So this tension, I'm just going to call it T2 for that overall pulley. Now we got to think, how can I relate this T1 and this T2? If I look at any of my other bodies that I've got on the diagram over there, I do have one, and this is a blast from the past from statics, from our pulley problems in statics, where if I look at pulley C, and I take a free body diagram, make a free body diagram of our pulley at C, what I'm going to find is that I have the tension of the orange cord that connects to A, T1, coming down off of that, while I also have the brown rope that connects through the pulleys, T2, on either side. And so I have brown rope and orange rope that connect into pulley C, giving me a free body diagram that looks like this. So now what I'm going to do is I'm going to note my kinetic diagram. And for my kinetic diagram, I'm just going to say, you know what, everybody, we're just going to assume acceleration downwards. Right? We're just going to blanket statement, kinetic diagram. We said that downward is positive, acceleration, downward, positive direction. That's what we're going to assume. And we're going to take that and we're going to work with it in each of these individual case scenarios. So because we have 3 separate free body diagrams, we can create 3 separate uses of our equations of motion. So I can have, for A, my sum of forces equals mass times acceleration. I can do the same thing at B, and I can do the same thing at C. Right? These are all unidirectional. They're all just moving up or down. So I don't need to do the X, Y, Z's. I'm just going to say, I mean, you can if you want to. You can label them as Fy equals MAY. But I know I'm only working in this up-down direction. Whatever you want to call that. So at A, my sum of forces at A is going to be, bearing in mind that downwards is positive. This is the coordinate system that we've set. Downwards is positive. Means I'm going to have the weight of the object, 981 newtons, minus T1, equals mass times acceleration. We release the block from rest. We're going to go ahead and assume that we have an acceleration at A. We're assuming it's moving downwards. We know the mass is 100 kilograms. That's multiplied by acceleration of A. Let's go ahead and look at B. So at B, I've got, once again, remembering downward positive means I have this weight of the block, 20 times 9.81, 196.2 minus T2 equals MA. Mass of block B is 20 kilograms times the acceleration of B. Let's keep moving. Let's take a look at C. Now at C, something very important that our statement said is that the masses of the pulleys and cords are neglected. Masses of pulleys and cords are neglected, which means when we set up this summation at C, it's really just a statics problem, right? If we neglect the mass of that pulley, then when I do the sum of forces here, T1 minus T2 minus T2 equals mass times acceleration. Mass is 0. So it doesn't actually matter what AC is. The mass is 0. And then this goes ahead and acts like a statics problem, where we get T1 equals 2 T2. Now if we bring it all together, let's look at all of those equations that we have. I have an equation with T1 and acceleration A in it. I have an equation with T2 and acceleration B in it. And then I've got a relationship for T1 and T2. And I've got a relationship for acceleration of A and acceleration at B. That's 4 equations, 4 unknowns. Means I can come together and solve for what I was looking for. And what we were looking for again in that problem statement, acceleration of B. Acceleration of B. This is the bad boy we're looking for right here, acceleration of B. So what I'm going to do is I'm going to take this equation and substitute it in. And I'm going to take this equation, substitute it in. Right, so that way I'll only have equations with T2s, and I'll only have equations with ABs. When I do this substitution, 981 minus 2T2 equals 100, and then I'm substituting in negative 1/2 AB. And then that second equation I kept totally the same. And that one I can solve for T2 if I want to. I can say the second equation, T2 equals 196.2. This is plus. No, this is negative. Wait, add to that side. Negative 20 AB. So now I'm going to substitute this T2 value into here. And I'll be able to have everything in terms of AB. I'll be able to solve for AB. 981 minus 2 times 196.2 minus 20 AB equals 100 times negative 1/2 AB. So when I go ahead and do the algebra, solve for AB, I get my acceleration in the B direction is negative 6.54 meters per second squared. And why is that guy negative? Why is that acceleration negative? It's because in our kinetic diagram, we had assumed that all accelerations were moving down in the positive direction. So positive direction was down. We assumed everything was accelerating in the positive direction, but B is not. B is actually going to be shooting up while A is moving down, right? A is much heavier than B, so it's going to want to move downwards while B is being forced upwards. So it tells us that our B is accelerating upwards, negative 6.54 meters per second squared. So these problems take a lot of manipulation. They take some time to find these relationships between our forces and accelerations and our kinematics. But in the end, they help us solve a lot more complex problems. And in our next video, we're still going to be working with this idea. So this isn't the only time you'll see it. In our next video, we'll do this same kind of concept, but now using curvilinear motion and using our normal and tangential components.